Good evening, dear students. Today is the third lecture of our series in functional materials. So this lecture will contain two parts. That is, one is energy materials, where I'll cover the remaining portion of supercapacitors and fuel cells, and this will be followed by our lecture on magnetic materials. So coming to what we will cover in the supercapacitors and fuel cells. In supercapacitors, we'll talk a little bit about the electrochemical double layer capacitors, pseudocapacitors, and hybrid capacitors. And then we'll discuss a little bit on the concept of fuel cells. This portion will not be covered as extensively as batteries, but we'll just give you an overview. So before we go into supercapacitors, it is important to refresh the memory that what we mean when we talk about electrolytic capacitors. So what is a capacitor? You have two parallel plates with dielectric in between, and the capacitance is limited by flat surface area and the dielectric properties. So capacitance is given by this equation, which you can see over here. C is equal to epsilon R epsilon 0 A by B. So C is nothing but the capacitance, A is the area, and epsilon R is the relative static permittivity, epsilon 0 is the permittivity of free space, and D is the distance. That is the distance between these two plates. So this is what the concept about electrolytic capacitors. So in one part, what you have is this air, as you can see over here, and the other part is when you are having the dielectric in between, and the capacitance increases because of the dielectric material which you have kept in between these two plates. So if we look into the history of supercapacitors, it was first noticed in 1957 by General Electric. There is an electrical double layer capacitor. Then Standard Oil of Ohio, they rediscovered this effect in 1966. And then in 1978, it marketed its product as a supercapacitor. So as you can see, from 2008 to 2020, the global supercapacitor market size has increased to almost around $800 million. And the growth you can see is almost at around 40%. So that is the way it is growing, this particular market of supercapacitors. So when we talk about supercapacitors, what we mean? The energy storage in supercapacitors is mainly in the interface between the electrode and the electrolytes. As you can see, this entire thing between the electrode and the electrolyte. So this energy storage method, it has a great relationship with the electrode material you're using, obviously, because it is dependent on that interface region between the electrode and the electrolyte. So the basic principle of supercapacitor is to store electrical energy through the electric double layer capacitance, which is formed by the charge separation, which is in the interface between the electrode and the bath solution. And the bath solution is nothing but your electrolyte. So supercapacitor can achieve higher capacitance because of thinner dielectric and higher surface area of electrode. So these are the two factors on which your capacitance value is going to depend. If you have a thinner dielectric material and you have a higher surface area of the electrodes. Compared to the capacitors, the supercapacitors, they have a larger area for storing more charge, and the capacitance is always in the range of almost in the farad range. So they store more energy than the electrolytic capacitors, where the capacitance is generally in the range of microfarads. So the supercapacitors, they have a very low leakage current, and they are suitable for many applications which operate in the voltage range of 1.8 to 2.5 volts. And the life of a supercapacitor is around 10 to 20 years, but the capacity, it generally reduces within 8 to 10 years, but you can still continue working with that supercapacitor for another 5-7 years. So the capacity is reduced to about by 20% in the first 8 to 10 years of operation of a supercapacitor. So if you look into the diagram of a capacitor vis-a-vis that of a supercapacitor, as you can see over here, this is filled with the dielectric material. The distance, as you can see, is little more. In case of supercapacitor, what you find over here is this corrugated surface. So basically it is having a lot of surface area, as you can see. Because of the increase in surface area, there is an excess storage of charge. And the separation distance is a little less compared to that what you find in capacitors. And obviously, so this is the reason why, because of that high surface area and the very thin dielectric material, whichever you're using, that is the reason why supercapacitors, they store much more charge compared to that of the capacitors. So now coming to taxonomy of the supercapacitors, which is the different kinds of supercapacitors you have. One is the electrochemical double layer capacitor. What is this? In this, the mechanism is that electrostatically ion adsorption or desorption happens at the interface of the electrode or the electrolyte. So this is the electrochemical double layer capacitor. So here it is electrostatic ion adsorption and desorption. Now come to the other type, which is a pseudocapacitor. As you can see over here, the pseudocapacitor, here the mechanism is reversible Faradaic redox reaction between electrolyte ions and the electroactive materials. So in this case, what you have is a redox reaction happening, which is Faraday. In electrochemical double layer capacitor, it is non-Faraday. And then you have something which is straddling between these two, which is a hybrid capacitor. In that case, you have an electrochemical double layer ion adsorption, desorption, and a reversible Faradaic reaction taking place. So now when I tell you this about the taxonomy, it's very difficult to understand. So we'll just look into the different kinds of materials which is used. So it is going to give you a little more idea about what I'm saying. So look into the charge storage systems. The charge storage system, it differs in these three different capacitors, supercapacitors. So the electrochemical double layer capacitor, EDLC as it is known as commonly, it stores energy, as I said, using ion adsorption. So there is no Faradaic or redox reaction happening. So in this particular case, it's very important to have a very high specific surface area of the electrode. And that's why mostly carbon is used. In this case, you will find that the capacitance value is around 100 to 120 farads per gram when you're using a non-aqueous electrolyte, and it's 150 to 300 farads per gram when you're using an aqueous electrolyte. So as you can see over here, all this magnified images are shown that how you are basically increasing the specific surface area of the electrodes. So what are the different kinds of materials which has been used over the ages? One is carbon aerogel. Aerogel is what? It's a very low density solid which is derived from gel that has had the liquid component replaced with a gas. So it is composed of nanometer sized particles which are covalently bonded together. It has very high porosity and it has a large surface area around 400 to 1000 meters square per gram. So you can use carbon aerogel as an electrode. Other very commonly used material is activated carbon, which is extremely porous. It has a very high surface area, and the area allows more electrons to be stored than any other conductor. So activated carbon is widely used in supercapacitors. Then you have another kind which is known as double layer electrolytic capacitor, which is by using carbon nanotubes. So you replace the activated charcoal with carbon nanotubes. It is aligned in a regular pattern. As you can see over here, it is aligned in a very regular pattern and it exposes a much larger surface area. So it dramatically increases the effective area of the electrodes and so it increases the power density. So this is another way in which you can improve on the capacitance value. Then, of course, we come to the other part, which is the pseudocapacitors, which store energy using fast surface redox reactions. So redox reaction, they occur at the surface of the active material. And what are the different kinds of active materials you use over here? They are metal oxides. So you can have ruthenium oxide, you can have Fe3O4, which is iron oxide, MnO2, manganese oxide. And you can have different conducting polymers like polyaniline, polypyrrole, polythiophene, etc. So in the metal oxides, the capacity value you can see is very high. It goes up to around 1300 farads per gram in case of ruthenium oxide, the nominal voltage around 1.2 volt. In case of the conducting polymers which you use on which you are spreading this particular oxide material, the capacities are around, for the conducting polymers, the capacity is around 30 to 40 milliampere hour per gram and it's a nominal voltage of around 1.0 volt. So this is pseudocapacitor. So as it's very clearly evident from the last two slides that in pseudocapacitors, the capacitance value is definitely much more compared to that of your EDLC. So if you look into the history of electrode materials for supercapacitors, stage 1 in 1957, when it started, you had carbon fibers, you had carbon aerogels, activated carbons, carbon nanotubes. From 1971 onwards, which you consider as stage 2, you had metal oxides, which are basically the ones which are being used for the redox reactions or the Faradaic reactions, and you had conducting polymers. This is from stage 2. Whereas stage 3, which started from 1993 onwards, it's the composites, which combine both of these, the good points of the EDLC as well as that of your Faradaic reactions. So you have various carbon materials and metal oxides, and you have various carbon materials and conducting polymers. So this is how the electrode materials for supercapacitors, it evolved over the years. So now, of course, we talked about batteries extensively in the second lecture. And now we had a little bit idea about the supercapacitors. So how are they related? I mean, how are their properties related to each other? That's very important to know. So here I have given you a particular plot, which is voltage versus time. In case of a double layer capacitor, you see how the charge discharge is happening. This is given in blue, whereas in case of a battery, if you look into the charge discharge, the time, you see the voltage is very much constant, whereas in a double layer capacitor, it is not so. So the charge time in case of an electrochemical capacitor, it is like 70% of it is charged in seconds, whereas battery, it takes at least an hour to charge. Discharge time is very short for a capacitor, whereas for battery, it is long. You can have a long discharge happening in the battery. Then charge discharge cycles, you can see in case of a capacitor, it is very okay to run from, some 100,000 to 1,000 cycles. Whereas in case of battery, it is only 500 to 1,000 cycles. And for the very good ones, which you see now for the lithium-ion battery, they sometimes go up to 1,500 to 2,000 cycles. Pollutants, in case of electrochemical capacitor, we'll say none, whereas in case of battery, we'll say the metals. But this none I would dispute, because if it was only carbon, then it was fine. But in this case, you do have these metal oxides coming in, so some metal amount of pollutants will be there. So if you look into the properties for supercapacitors, you have a higher power density, whereas in batteries, you have a higher energy density. Supercapacitors, they have a much faster charge and discharge rate. Then it is environmentally friendly. It has an extremely low internal resistance. It has a high efficiency of around 97 to 98%, and it has over 1 million charge discharge cycles. Whereas when you look into batteries, typically the charge discharge cycles goes from 500 to 1500. And it contains very highly reactive and hazardous chemicals, as you know, for the electrolytes and all. And then you have these lithium dendrites forming, and then fire hazard and stuff like that. And of course, it is negatively affected by low temperatures because of the dendrite formation. So now looking into the different application of supercapacitors, it is used extensively, backup for uninterruptible power supplies. Then you have lightweight power supplies for small aircraft. Then it provides short duration power for various vehicle systems, such as when you're braking a car or you're steering using the steering wheel. That short burst of power is generally given by the supercapacitors. Then it is used to absorb power during short periods of generation, such as in case of regenerative braking. And then it also extends the range and battery life in hybrid electric vehicles. That's a very important application of supercapacitors. So yeah. And then for the hybrid electric vehicles, CSIRO in Australia, this is a national science agency, they have developed an ultra battery which combines a supercapacitor and a lead acid battery in a single unit. So it has almost 4 times longer life cycle. It has 50% more power and 70% cheaper than batteries, which are normally used in the hybrid electric vehicles. So supercapacitors having a lot of application in hybrid electric vehicles. Now coming to the second part of the energy materials, which is your fuel cells, second part of today that is. So it's a fuel cell. So what is a fuel cell? It's an electrochemical device that converts chemicals like hydrogen and oxygen into water and produces electricity in the process. So fuel cell, ideally, as long as you are providing the reactants, which is hydrogen and oxygen, it is supplied to the fuel cell, it will continually produce electricity and never go dead. So unlike the conventional batteries, so you can say it is an inexhaustible supply of power if you are having an ideal fuel cell. So there are different types of fuel cell. One is based on the type of electrolyte you're using. So you can have alkaline fuel cell, you can have a phosphoric acid fuel cell, a polymer electrolytic membrane fuel cell, which is PEMFC, or which is also known as a proton exchange membrane fuel cell. You can have a molten carbonate fuel cell, or you can have a solid oxide fuel cell, that is the SOFCs. Then you can also demarcate the fuel cell types based on the type of fuel and oxidant you are using. So you can have pure hydrogen oxygen based fuel cell. You can have hydrogen rich gas and air based fuel cell. You can have ammonia and air based fuel cell, synthesis gas and air based fuel cell, as well as hydrocarbon, which is in the gaseous form, and air as fuel cell. And then there is another fuel cell which is based on operating temperature. So you can demarcate, different kinds of fuel cells. So we'll take a few examples. So if you have a polymer electrolyte fuel cell type, then the electrolyte which is used is a polymer membrane. The operating temperature varies between 60 to 140 degrees centigrade, and the electrode reactions are shown over here. As you can see, in all cases, most of the cases, you have hydrogen and you have oxygen. In some cases, you have methanol also. So when you're using a direct methanol fuel cell type, again, the electrolyte is a polymer membrane. Operating temperature is lower, so it is from 30 to 80 degrees centigrade. For an alkaline fuel cell, the electrolyte used is potassium hydroxide. The operating temperature is a little high, from 150 to 200 degrees centigrade. With an acid like a phosphoric acid fuel cell, the electrolyte is phosphoric acid. Operating temperature again ranges between 180 to 200. For a molten carbonate type fuel cell, the electrolyte which is used is either lithium carbonate or potassium carbonate, and the operating temperature is around 650 degrees centigrade. The corresponding electrode reactions I am not reading out, you can go through it. And in the solid oxide fuel cell, you have the electrolyte which is an yttria stabilized zirconia, and the operating temperature is around 1000 degrees centigrade. Okay. So only one particular fuel cell operation I'm showing over here, which is the solid oxide fuel cell. In this case, what the electrolyte which you're using is a solid ceramic, which is generally zirconium oxide, which is stabilized with yttrium oxide. And instead of liquid, instead of any kind of liquid electrolyte, and it operates at a high temperature at around 800 to 1000 degrees centigrade. So you see how it works. So cathode, an anode, and an electrolyte is sandwiched between this cathode and anode. So it has a cathode, it has an anode. The electrolyte is sandwiched between them, and this electrolyte is a solid ceramic electrolyte. So oxygen from the air, it is flowing through the cathode. A fuel gas containing hydrogen, it is passing through the anode. So what happens, the oxygen ions, as you can see over here, it is migrating through the electrolyte and it reacts with the hydrogen to form water. And this water reacts with the fuel to form carbon dioxide and hydrogen. So ultimately what you get is carbon dioxide and hydrogen. And the electrons from the electrochemical reaction, it flows from the anode to the cathode through an external load. So you have this anode to the cathode. As you can see over here, from anode to cathode, this electron is flowing in this direction and through an external load. So as long as the reaction is happening, as long as you are having the flow of oxygen and the fuel gas continuously, you are able to generate this electrons flow from this electrochemical reaction from the anode to the cathode through an external load. So when we look into a polymer electrolyte membrane fuel cell, which we discussed among the different types of fuel cell, in this case, the electrodes, the anode and the cathode, they are separated by a polymer membrane electrolyte. And each of these electrode is actually coated on one side with a thin platinum catalyst layer. The electrodes, catalyst and membrane, they form this entire membrane electrode assembly. Hydrogen and air are supplied on either side through channels formed in the flow field plates. So this is how the working diagram of a PEMFC would look like. So what are the advantages of fuel cells? Definitely they have a very high efficiency, they are modular, they are quiet, they are non-polluting, combined heat and power is generated, it's load flexible. So fuel cells using methanol and oxygen are currently being developed. They are used extensively in space program as sources of DC power, direct current power. And they are very efficient and they are capable of providing hundreds of kilowatts of power. So with this, we come to an end for our energy materials. So giving you a small recap of what we did. We first spoke a little bit about the electrochemistry part. We kind of charted down the history of the various high points in electrochemistry. And then we spoke a little bit about batteries. We talked a lot about electrode materials and why these different electrode materials are being used. We spoke about the different kinds of cathodes we used in the battery, which are basically layered materials, olivine materials, spinel type of materials, which we used as cathodes. And we spoke a little bit about anodes, the anode materials which we normally use for battery, which is like graphite, which we are using in case of lithium-ion battery. And the other conversion kind of material which we are using in case of anodes, which gives you much higher capacity compared to that of the intercalating material like graphite. And then we spoke a little bit about how the efficiency of a battery can increase. What are the ways you can improve the efficiency of a particular battery? Then we spoke about after how to assemble a coin cell using these different electrode materials and electrolyte, how you are going to assemble the coin cells. And then from the coin cells, we came to how you can test the coin cells. So we spoke a little bit about cyclic voltammetry, and then we covered a little bit about electrochemical impedance spectroscopy. We spoke a little bit about galvanostatic charge discharge measurements. All these points we covered. And after that, what we have done is a little bit we touched upon the supercapacitors, and then we talked a little bit about fuel cells. So this is regarding the energy materials, the type of materials which are normally used in case of supercapacitors. We talked about in the fuel cells, what are the different electrodes and the electrolyte we use. We touched upon a little bit on that. And we gave you a kind of an overview about the properties of these different energy storage devices, and which one is giving you more power density, which one is giving you more energy density, where they are being applied. So all this has been covered in your energy materials. And with this, we end the energy materials part, and we now move on to magnetic materials. So what we will cover in magnetic materials is magnetic moments of electron and free atom. We'll talk about dia, para, ferro, ferri, and antiferromagnetism. We'll talk about theories of paramagnetism and ordered magnetism. We'll talk a little bit about magnetic phenomena like hysteresis and related properties, magnetic anisotropy, magnetostriction, magnetoresistance, superparamagnetism, then magnetic domains, domain theory, magnetization process in terms of domain theory. So these are the different points which we will try to cover. So before that, as I did in case of energy materials, a little bit about the history of magnetism. So the first known magnets were naturally occurring lodestones, which is type of iron ore, which is called magnetite. So people of ancient Greece and China discovered that a lodestone would always align itself in the longitudinal direction if it was allowed to rotate freely. And this property of lodestone allowed for the creation of compasses 2000 years ago, which was the first known use of magnet. And it was on the basis of these magnets, basically the entire exploration of the earth started. So in 1263, Pierre de Maricourt, he mapped the magnetic field of a lodestone with a compass, and he discovered that a magnet had two magnetic poles, that is the north and the south poles. In 1600s, then William Gilbert, he was a physician of Queen Elizabeth I, he concluded that Earth itself is a giant magnet. And in 1820, the Danish physicist Hans Christian Ørsted, he discovered an electric current flowing through a wire. It causes a compass needle to deflect, showing that magnetism and electricity, they were related. Then Michael Faraday in 1830 and Joseph Henry, they independently discovered that a changing magnetic field produced a current in a coil of wire. Then Maxwell in 19th century, he was a Scottish physicist. He mathematically unified the electric and the magnetic forces, and he also proposed that light was electromagnetic radiation. Then in the late 19th century, Pierre Curie discovered that magnets lose their magnetism above a certain temperature, and now we know that as a Curie point. And in 1900, scientists discovered superconductivity. So superconductors are what? They are materials which have zero resistance to a current flowing through them when there is a very low temperature. So, and they also exclude magnetic field line, which is known as the Meissner effect, and this makes magnetic levitation possible. So all these bullet trains which are running on magnetic levitation, it is thanks to all this superconductivity. So coming to a little bit of the basics before we go into the details of magnetism. So refreshing your memory. Electric fields due to electric dipole, they affect any charge in the vicinity, but the difference with the magnetic field is that the magnetic field, it affects only moving charges. So as with the charges, in case of magnetic poles also, the opposite poles they attract and the like poles they repel. So the force exerted on a charged particle by a magnetic field is given by the vector cross product of QV cross B, where Q is nothing but charge on the particle. It's a scalar quantity. V is velocity of the particle, which is related to the field, and it's a vector quantity. Your capital B is magnetic field, or it's a vector quantity, and theta is the angle between this QV and your B vectors. So the force which is exerted on a charged particle is given by this particular cross product. Now coming to a few, the magnetic for the SI units. So you have one Tesla, which is normally the magnetic field strength. It's a very powerful magnetic field. It is 1 Newton per ampere meter. And because Tesla is such a powerful magnetic field, many times you find in many of the books, it is Gauss which is used, which is 1 by 10,000 of Tesla. Earth's magnetic field at the surface, it varies, but the strength is around 1 Gauss. So now the origin of magnetism, how magnetism actually originates. Macroscopically, it is through charge and currents, whereas microscopic, it originates the atomic scale. So if you have a loop of area A which is carrying a current I, the intrinsic intensity of the magnetic field is given by the magnetic moment vector, which is given as m or mu, and directed from the north pole to the south pole. So the magnitude of m, or this magnetic moment vector, is I multiplied by A. So the magnetic moment is a measure of the strength of the magnet and is the ability to produce and be affected by a magnetic field. So now coming into a few important quantities in magnetism, which I will be using very often. So I'll just refresh your memory with that. Magnetic moment vector, the units is joules per Tesla. It basically measures the strength of the magnet. When I talk about magnetic moment vector, it measures the strength of the magnet. Then magnetic field strength or magnetizing force, capital H. Its unit is ampere per meter, and it is measure of the strength of the externally applied field. Then you have magnetization, which is magnetic moment per unit volume. And this measures the material's response to an applied field H. Then you have magnetic induction or magnetic flux density, which is magnetic flux per unit area. And this magnetic flux density inside the material, it is given as capital B equal to mu 0 H plus M. And this mu 0 is the magnetic permeability of vacuum. Then you have permeability. Permeability is given as B by H, and it is dimensionless. Then another very important term, which is the magnetic susceptibility chi, which is M by H. And this is also sometimes known as mass susceptibility when you give it as chi M, or molar susceptibility when it is chi in capital M. So these are also used. So the susceptibility is basically, it is like permeability, but it is a better quantity compared to permeability. Why? Because it gives a feel and a physical picture of the type of magnetism involved. So, and then you have energy of magnetic moment, which is given as minus m dot b, which is a scalar dot product. And then you have magnetic anisotropy, which is another term which I'll be using quite often. So anisotropy means that various directions in the crystals, they are non-equivalent with respect to magnetization. So this implies that m, it might not be the same in all directions of the applied field. So there are many contributions to this anisotropy. Crystalline anisotropy or magnetocrystalline anisotropy is the most prominent among them. So now coming to the response of a material to a magnetic field. So this is basically known as magnetic susceptibility, which is delta M by delta H, or it is given as M by H, where M is magnetization and H is the magnetic field. So classification, if you do, of materials based on its response to a magnetic field, you have in broad two types. One is paramagnetic, which is attracted by a magnetic field, diamagnetic, which is repelled by a magnetic field. So what are the sources of magnetism which we were discussing? So we have seen charges in motion, as in current, it produces magnetic field. So that is one source of magnetism. Another source is the electron itself. Electrons will behave as if they are tiny magnets. So you have a spin magnetic dipole moment, which is due to, the spinning of the electron on its own axis. And then you have an orbital magnetic dipole moment, which is basically when the electron is moving around the nucleus. So it is not exactly like little balls and rotating, as you know, but it's easier to visualize it in that particular way. So here it is a pictorial description how your spin magnetic moment is coming in and how your orbital magnetic moment is coming in. So when you have the origin or the atomic origin of magnetic moments, you can have the spin coming in of the electrons as well as the orbital motion of the electrons, and you can also have the spin of the nucleus. So nuclear spin is very slow and it has a very small contribution to the overall magnetic effect. It only becomes a little considerable only when your temperature is very low. Otherwise, it is mostly contributed by spin of the electrons and the orbital motion of the electrons. And the magnetic moment due to spin is equal to the magnetic moment due to orbital motion in the first Bohr orbit, and it is approximately expressed in terms of Bohr magneton. So one Bohr magneton, as you can see over here, is EH by 4 pi m, and the value is given over here. So if you want to understand magnetism, you have to understand the effects which are observed. So one is direct coupling. So moments, which is the spin or orbital motion or nuclear, localized to an atom, and they directly interact with moments in neighboring atoms. So that is a direct coupling. Then you have a mediated interaction. In this case, what happens? The moments which is arising from an itinerant electron in the bands of metals, so they have a possibility of mediation of interaction via different free electrons. And another is a super exchange. So here, the local magnetic moment interacting with other local moments. In this case, the mediation is via non-magnetic elements, or that's why we call it a super exchange. So you probably have a magnetic material, and then you have a non-magnetic material followed by another magnetic material. And then you have what is known as mostly antiferromagnetism, as you see in manganese oxide. That is a result of super exchange, where manganese and oxygen, they are kind of alternating, are present in alternating layers. So one is magnetic, the other is non-magnetic. So from magnetism of the fundamental components to magnetism of devices, how we move. So this is the thing. So fundamental components of magnetism is mu orbit and mu electron. Then you have the one which is having due to the spin of the electron. Then you have one which is arising due to the spin of the nucleus. So all these components make up the magnetism of the atoms. Combined together, they can give you magnetism of molecules, and together they give you magnetism of solids. And this is ultimately, it gives rise to something which is known as giant magnetoresistance, which is known as magnetism of hybrids. So now looking into the different interactions, spin and the orbital motion, when they are interacting with each other, it is a weak interaction. Spin, it is when it is interacting with the lattice, that is also very weak. The strong one is the interaction between the lattice and the orbital motion. This is a very strong interaction. So now the other parameters which we use to comprehend magnetism in the solids, the effect of external magnetic fields, which is diamagnetism and polyparamagnetism. These are effects of the external magnetic field and they do not arise independently from fundamental atomic entities. An effect of temperature, where the ferromagnets, when we heat, they become paramagnet at a particular temperature. So alignment of the magnetic moments in the paramagnet by this is due to a field and it is thermally assisted. Now the different types of magnetism, all matters, they show diamagnetism. In some cases, it arises out of band structure of metals, which is due to, and these are the different types of magnetism, which say one is polyspin paramagnetism, then we have band ferromagnetism, and then you have band antiferromagnetism. All this arises due to band structure of metals. And then you have something which is arising out of the atomic magnetic moments, which is permanent, and this arises due to the spin and the orbital motions. So when it is non-interacting atomic moments, you have something which is known as Curie paramagnetism. Whereas when there is interacting atomic moments, you get to these things which are known as ferromagnetism, ferrimagnetism, and antiferromagnetism, ferromagnetism. So what is diamagnetic? In case of diamagnetic, you have paired electrons. In this case, the permeability or your susceptibility is negative. It is temperature independent. A few examples are shown. So if you place a material which is diamagnetic between magnetic lines of force, they kind of repel each other. In case of paramagnetic, you have unpaired electrons. In this case, the susceptibility is positive. It decreases with temperature. Few examples are shown. And whenever you have a paramagnetic material placed in an external magnetic field, you can see it attracts the magnetic lines of force. And this is how the susceptibility value is going to change with temperature. As temperature increases, the susceptibility value it decreases. And this is basically nothing but your Curie's law. So this is simplified understanding of diamagnetism based on Lenz's law. So in this figure A, this is the figure A, the electrons paired in the same orbital, they move with a velocity v, and they are, as you can see, they are cancelling each other. So M1 is cancelling M2. When you are having a magnetic field B applied on the magnetic moment, you see the M1 is increasing, whereas the M2 is kind of decreasing. So the net magnetic moment, what it is doing, it is opposing the magnetic moment which is externally applied, which is B. So in this case, if you look into the image plot for a diamagnetic substance, as you can see, with application of the magnetic field, your magnetization value, it decreases. So this is basically the idea of diamagnetism. In paramagnetism, there are two distinct types of paramagnetism. One which is arising from atoms, molecules, which has a net magnetic moment, and the other which comes from band structure, which is polyspin or weak spin paramagnetism. So if the net magnetic moments in the atom molecule, they are not cancelling out, then the material is paramagnetic. Oxygen, it has a net magnetic moment of around 2.85 Bohr magnetons per molecule. So you have to understand one thing, that even though there are many electrons in the atom, most of the moments they are cancelling out. Okay. And what you have left are very resultant little few Bohr magnetons are there. So if there is an absence of external field, then these magnetic moments will also point in random directions, and the magnetization of the specimen is going to be zero. However, whenever you are applying an external magnetic field, then there are two factors which come into the picture. One, the magnetic field which is there inside that particular material, it aligns to the external magnetic field. And the other is when the temperature is getting disturbed, in that case, when the temperature increases, there is a disordering tendency of the temperature. The higher the temperature, the disordering phenomena, it increases. So these are two different factors which come into picture. So the combined effect of these two factors is that there is only a partial alignment of the magnetic moments, And the susceptibility of the paramagnetic materials, it has a very small value. For example, for oxygen, it is only to the extent of around 10 to the power minus 6 meter cubes per kg. So now these two types of paramagnets, it can be differentiated. Those which are always paramagnetic with no other details to be considered, and those which are ferromagnetic, ferrimagnetic, or antiferromagnetic, and they become paramagnetic on heating. So these are two different kinds of paramagnets. One, they are paramagnetic, they are paramagnetic always. In the other case, you have these cooperative phenomena like ferromagnetic, ferrimagnetic, and antiferromagnetic, which we'll discuss now. So these will have a non-zero value of theta in the Curie-Weiss law. Curie-Weiss law is what? Curie law, you saw, is chi is equal to C by T. When you have a Curie-Weiss law, is this theta parameter comes into the picture. And this is because of that cooperative phenomena which you see in different kinds of paramagnetic material. So any magnetic alignment, which is an ordering phenomena, is always fighting against the disordering effect of temperature. So while mass susceptibility is independent of temperature for a diamagnet, for a general paramagnet, it will follow the Curie-Weiss law as is shown over here. So in this case, this chi m is nothing but your mass susceptibility. C is Curie constant, and theta is in units of temperature and is a measure of the interaction of the atomic magnetic moments. So actually, molecular field or is a force or torque tending to align this adjacent atomic moments. And its typical value is around 10 to the power 9 amperes per meter, and it is much stronger than any continuous field which is produced in a lab. So if there is no interaction between the atomic magnetic moments, then theta is 0 and the Curie-Weiss law reduces to the Curie law. The variation of the susceptibility for these kinds of behavior is shown in this particular diagram, as you can see over here in this particular plot. So in a Curie law, you start from 0 and you see this is the way the susceptibility changes with temperature. Whereas in case of a material which is ferromagnetic, in that case, it is going to show you this kind of Curie-Weiss law. In this case, you will have this definitely a finite theta value. Whereas in case of a totally simple paramagnet, in that case, the theta value is around 0. So the cooperative magnetic interactions, we talked a lot about ferromagnetism and all. So how is ferromagnetism? This is a cooperative, they are all aligned. In case of antiferromagnetism, you have one upspin followed by another downspin. In ferrimagnetism, you do have up and down spin, but the magnitude of the magnetization vector, they vary. So in case of this, the Curie-Weiss law, you can write as chi is equal to C by T plus minus theta. So the theta value can be positive or the theta value can also be negative. So now let's see what we mean by that. So if you plot 1 by chi versus T in case of a paramagnet, what you see is a straight line which passes through the origin. Fair enough, because in this case, the equation is chi is equal to C by T. Whereas in case of a ferromagnet, if you see this 1 by chi versus T, you see a straight line, but it doesn't pass through the origin. It passes through some finite value of T. And that finite value of T is nothing but your theta value. So that is your nothing but your Curie temperature or that theta value, whatever you see. In case of antiferromagnetism, what happens is 1 by chi versus T, if you look, you will get a straight line, and if you extrapolate that straight line, it will cross at some negative point over here at the temperature axis. So this is antiferromagnetic, and that particular temperature is known as the Néel temperature, named after the scientist who discovered it. And then you have something which is known as ferrimagnetism. In this case, you do see a straight line, but there is a slight little curve at the bottom in this portion. And this is because of the difference in the magnitude of these vectors, which are kind of opposite to each other, the magnetization value of this particular vector. So you see this kind of a tilt in this particular line, 1 by chi versus T. So now coming to a very important property of ferromagnet, which is magnetic hysteresis. So what it happens, you have when you are actually plotting the magnetization versus the magnetic field. In this case, as you are increasing the magnetic field, the magnetization value, it increases. When you decrease the field, it doesn't go back to 0. It still has some kind of magnetization left in it, which is known as the remanence value. As you can see over here, this is that remanence value. And then to bring back that magnetization to 0, you have to apply magnetic field in the opposite direction. And when it reaches 0, this particular field, whatever that H value, this is known as the coercivity or the coercive field Hc. So this is a very typical property which is exhibited by any ferromagnet. And why this happens? It is because of the presence of all these magnetic domains. So normally when you have a magnetic material, it is divided into different domains, and all these magnetization values, what are the aligning direction, they are pointing in different directions. This is how a normal magnetic material is going to look like. The moment you have an external field applied to it, then all these magnetic moments start aligning itself to that external magnetic field. And that is why that magnetization value, it increases. But when you bring back, then the story is very different and you still have some magnetization left in it. So if we apply sufficient magnetic field to produce complete saturation inside the ferromagnet and then start reducing the field back to zero, we find that at zero applied field, some residual magnetization or remnant induction will remain, and it will take a significant field, which is coercive field, to completely demagnetize the material. So if you can see the coercive field in Oersted and relative permeability for different metals, which has been plotted in this particular plot. And you will find a very nice correlation over here. Materials which has a very large magnetic permeability. You look into here, very large, like med glass and all, the coercivity is really very, very less. So when you have a very large saturation magnetization, they exhibit a very small coercive field, and vice versa. Again, you have these magnets like samarium, cobalt, and iridium iron, those kind of magnets when you have, in that case, the coercivity value is very high, but the relative permeability is much, much low. So now we come to something which we have discussed a little while ago, that was in the different terms which you are going to use very often. So one is magnetic anisotropy. So what is magnetic anisotropy? I gave a small definition: the dependence of the magnetic properties on the direction of the applied field with respect to the crystal lattice. So it turns out that depending on the orientation of the field with respect to the crystal lattice, one would need a lower or higher magnetic field to reach the saturation magnetization. So the saturation magnetization, it is not the same in all the directions. It changes along the directions. So we have something which is known as easy axis, and then you also have something which is known as hard axis. What is easy axis? As the term signifies, it's a direction inside the crystal along which, when you apply a very small magnetic field, it is sufficient to reach the saturation magnetization. Whereas hard axis is just the opposite. So here you have to apply a large magnetic field to reach the saturation magnetization. So now let's see, this is an example given over here. You have a body-centered cube ion. So the highest density of atoms is in the 1-1-1 direction. So in the 1-1-1 direction, as you can see, you have the highest density of the atoms. In contrast, the atom density is lowest in the 1-0-0 direction, as is shown over here. So what happens is, magnetization curve, when you use one particular direction, you're applying the external magnetic field, what you find is that the magnetization curves, they show that the saturation magnetization in 1-0-0 direction requires significantly lower field than the 1-1-1 direction. So here saturation magnetization is reached at this point when the magnetization value is here. Whereas when you are in the hard axis or the 1-1-1 axis, to reach the saturation magnetization, the external magnetic field applied is much higher. So that means the easy axis is one where it has less number of atom density, whereas the hard axis is one which is higher amount of atom density. So now you come to face-centered cubic nickel. In this case, the 1-1-1 is the lowest back direction, and it becomes the easy axis, whereas 1-0-0 is the hard axis. So typically, this is how your magnetization versus H curve is going to look in case of nickel. Around 1-1-1 direction in easy axis, you see at a much lower H value, you have reached the saturation magnetization. Whereas along the hard axis, which is your 1-0-0, in that case, you require a much higher magnetization, external magnetic field to be applied to reach the saturation magnetization. So for a material with a single easy axis perpendicular to the hard axis, which you would see in case of cobalt, which has a hexagonal cubic close packed structure, in this case, the lowest pack distance is the 0-0-0-1 is the easy axis, whereas 1-0-0, this is the closed pack direction, and it corresponds to the hard axis. So for a material which has a single easy axis perpendicular to the hard axis, then the energy associated with the magnetic anisotropy is given in this particular equation, as you can see over here. So in this case, you can see the magnetic anisotropy, the energy of the magnetic anisotropy is given by this, which is K mu1 sine square theta. And theta is the angle between the magnetization and the z-axis, and KUN is the anisotropy constant. So different anisotropy constants, as you can see over here. So magnetization versus field, typical measurement, you find the hysteresis loop. Saturation magnetization is basically the MS value. Coercitivity is HC, which is this particular value over here. This is the coercitivity. This is how a MH hysteresis loop is going to look. So now coming to magnetic anisotropy once again, for a cubic material, you have three z-axes, okay? And the anisotropy energy is written by this equation as you see over here. Here alpha is nothing but cos theta I, and theta is the angle between the magnetization and the z-axis. Always remember the theta is the angle between the magnetization and the z-axis. So the physical origin, what is the physical origin of this magnetic anisotropic energy? It is the interaction of the mean exchange field and the orbital angular momentum of the atoms or the ions in the lattice. So this interaction is referred to as spin orbit coupling. So you have a spin orbit coupling. So you have a magnetization angle, it is in this direction, it goes to the other direction, and while going from this to this direction, it generally this is rotating, as you can see over here. So then some energy is there, some anisotropy energy is needed, and this delta E value is Ku and V. Ku multiplied by V. So how do you derive the hysteresis loop for a single domain ferromagnet? How is it going to look? So we start with an anisotropic ferromagnet, sufficiently small so it has a single magnetic domain. Now we are going into the derivation of how this particular magnetic hysteresis, how this is coming in. So all magnetic dipoles, they are aligned in the same direction, maximizing the total magnetization. So if it's a single magnetic domain, all the magnetic dipoles are aligned in the same direction. So it maximizes the total magnetization. So please assume that the angle between the magnetization and the EZ axis is nothing but theta, as shown over here. Okay, so this is the EZ axis and this is your magnetization. So in the absence, when you are not having any external field, the energy of the ferromagnet as a whole is dominated by this anisotropy energy. So it will be given by this value which I showed before in the previous slide. This is Ku sine square theta. Now, when you have this external field which is applied to this ferromagnet, in addition to the anisotropy energy, you will also have a magnetostatic or Zeeman energy. And that is given by HMS cos phi minus theta. So what is H over here? It is the applied magnetic field. MS is the saturation magnetization. And phi is the angle between this applied field and your EZ axis. So now what happens is, your total energy is a sum of these two factors. It is Ku sine square theta plus HMS cos phi minus theta. So now there are two important special cases for the direction of magnetic field. It can either be along the z-axis or it can be along the hard axis. So when it is along the hard axis, this phi value is nothing but pi by 2 or 90 degrees. So in that particular case, when you are fitting that pi value, that's pi by 2 into this particular equation, what you have is that your E is nothing but Ku sine square theta plus HMS sine theta. So far so good. So now you have to find the angle theta that minimizes the energy in this particular case. So what is that angle where you will have the minimum energy? So for that D, you have to do the derivatives. D by d theta is equal to 0. And if you fit into this equation, you will find that this magnetization value, it has to be parallel to, or it has to be anti-parallel to the externally applied field. And when you do the double derivative of it, you will get the values, the theta values in between. This value is going to be the minimum. So you have the H value, which can be either less than minus 2 Ku by ms, or it can be higher than 2 Ku by ms. So these are the two different, theta values in which you will find this, the energy value to be the minimum. And the only way this condition can be satisfied is if your HA is 2 Ku by ms, or your this K or anisotropy constant is HAms by 2. So this HA is known as the anisotropy field, or field at which the magnetization reaches saturation. So for fields below this anisotropy field, from the equation d by d theta equal to 0, you also find that this 2 Ku sine theta plus HMS is 0. So for the component of magnetization, which is parallel to the applied magnetic field, we'll find the sine theta value is nothing but minus m by ms. So substitute this into the previous equation, and what you get is this m is nothing, the magnetization value is nothing but ms h by ha. So for a hard axis magnetization, it will change linearly with the applied field until it reaches saturation. So you derived something which is that when you are having a hard axis magnetization taking place, then when you are applying the applied field, it will change linearly with the applied field until it reaches the saturation point. Whereas when you are doing an easy axis magnetization, in this case the phi value is 0 because it is along the easy axis. So in this particular case, when you put phi is equal to 0, this is how your equation is going to look like. Now it is going to become HMS cos theta. Now again, the same way we have to find out the angle at which you will have the minimum energy. So you do the derivative, and with the derivative you find in this particular case, the magnetization value and the applied field, they have to be anti to each other. So in this particular case, when you're doing a double derivative, then the h value, it has to be either less than 2 ku by ms or more than minus 2 ku by ms. So energy will be minimized for all magnetic field values between these two. As you can see over here, minus 2 ku by ms between and 2 ku by ms. So the coercive field in this case is nothing but a sum of this, so it is 2 ku by ms, which is basically the coercive field, because in the other two places, that is beyond this point to this point, it is having the lowest energy. So all of these fields will yield saturation magnetization. So this results in the ideal rectangular shape of the hysteresis loop. So from this expression of the coercive field, which is Hc is 2 ku by ms, it is obvious that materials with high saturation magnetization would have low coercive field unless they have a really high anisotropy. So this ku value, if it is very more, only then you will find that otherwise in most cases it is basically if ms value is more, then Hc value is going to be less. Only the ku value, if the anisotropy is high, then you will find some difference that it will increase with the Hc value. But for a given particular anisotropy constant, as saturation increases, coercive value it decreases. So this is why you saw that first graph which I showed in over here. I'll just go back to refresh your memory in this case. So this kind of explains this relative permeability and the coercive field. So this is now mathematically explained to you. So now let's look into the ideal hysteresis loop. So when it is along the z-axis, it is this value. It is this how your hysteresis loop is going to look like. Whereas when your external field is along the hard axis, then it is somewhat like this. So this is how your ideal hysteresis loop is going to look along the z-axis. But you definitely don't have the magnetic field pointing along this direction or in that direction, it's somewhere in between. So that is the reason why you will see that curved formation of the hysteresis loop in case of ferromagnets. So in case of permanent magnets, what we see, it has a high coercivity and it also has a high remanence. So these are all hard magnets, and it also has a very high Curie temperature. Whereas in case of transformers, which we use are soft magnets, they have a low coercivity and they have low remanence. Information storage, we use soft magnets with very unique hysteresis loop, which looks somewhat like this, but we are not really discussing it right now. So now you see the alignment of domains which leads to the magnetization of sample. So most of the cases you see M versus H, when you plot it goes somewhat like this. So what is giving rise to this particular shape is what we are going to discuss now. So during magnetization, the domains oriented favorably, which is along the field direction, they grow at the expense of the unfavorably oriented domains. So you have this domain wall motion. This can occur by two different methods. One is the domain wall motion and another by the rotation of the magnetization of the domains. So these are two different methods by which it happens. So the largest improvement in the magnetization happened with the domain wall motion. So the external magnetic field, it tends to align the misoriented spins in the domain wall, leading to its displacement. And whereas when all the domain wall motion has taken place, then the entire domain wall rotation takes place. In this case, you find when the domain wall rotation occurs, the increase in magnetization value is not really much. So the maximum increase in the magnetization happens with the wall motion. So rotation of spin is normally opposed. This rotation of the spin is normally opposed by increase in anisotropy energy, that is magnetocrystalline shape or stress anisotropy. And during rotation, all spins need not be parallel to one another, and the actual picture, it can be a little complicated. So we are simplifying and we are explaining. Actual picture is sometimes a little bit more complicated than this. And then we look into the effect of temperature. We said that there are two different effects happening. One is of the external field, which is trying to align the domain walls and the magnetic moments. And the other is the effect of temperature. So we now discuss the effect of temperature. So you spatially correlated collective quantized modes, they lead to demagnetization. So ferromagnets become paramagnet above Curie temperature. So at Curie temperature, the susceptibility becomes, infinite. Even beyond Curie temperature, there are local clusters or spin clusters of aligned magnetic moments. So maximum magnetization is obtained when all the moments have parallel orientation. And this corresponds to magnetization which is known as M0 or the saturation magnetization. So if you plot something which is known as Ms by M0 versus T by Tc, for all this material, you will have, they will approximately lie on one another for all different materials. So if you have a plot of Ms by M0 and T by Tc of different materials, you'll find all of them overlap on this particular line. And this is known as a demagnetization curve for any ferromagnet. So now the domain structure and magnetization process, how it happens. So the magnetic structure of a ferromagnetic material, as I said, consists of domains. Why you need these domains? Because they reduce the magnetostatic energy. So domains, they are separated by walls. So there are two types of walls. One is known as a block wall and the other is known as a Neal wall. In the block wall, the spin vectors, as you see, this is a block wall I have shown over here. Here you see the spin vectors rotate out of plane in the domain wall. In the Neal wall, they will always rotate in the plane. This Neal walls you see only in thin films, whereas the domain wall thickness, normally they are a few hundred atomic diameters, so it is rather diffuse. So the domain wall itself is a nanostructure. So this is how the domain structure looks. So you have block walls, you have Neal walls, and Neal walls are generally seen only in case of the thin films. So the domain wall, it represents a region of high energy as the spin vectors are not in the direction of easy magnetization. So thicker walls represent higher energy. And in materials which has very high magnetocrystalline anisotropy energy, the domain walls are thin. That is around 10 atomic diameters is basically the thickness. Now, there are other sources of anisotropy also apart from this, and these are due to shape of the particle and due to residual stress which is present in the particle. So, a competition between the magnetostatic energy and the magnetocrystalline anisotropy energy, it essentially decides the domain size and shape. So, if the size is very much more, then you have a lot of magnetostatic energy coming in. If there are too many small domains, then again the magnetocrystalline anisotropy is also going to increase. So it is basically a balancing between these two which gives rise to the number of domains, its size and its shape. So the word essentially has been used. There are many other factors also which contributes to the energy, and these are like magnetostriction. They also contribute to the overall energy. So the total energy in case of this kind of magnetic ferromagnets or magnetic material, it is written as a sum of four different terms. One is exchange energy, the other is anisotropy energy, magnetoelastic energy, and then you have external energy. So external energy, it corresponds to energy of total magnetic moment in the external magnetic field. What is magnetostriction? So coming to magnetostriction, as the name suggests, this material is going to change shape when it is placed in a magnetic field. So phenomena, this involves a bidirectional energy exchange between magnetic and elastic states, and these materials provide a mechanism both for actuation and sensing applications. So magnetostrict materials, these are generally strictive materials, are used for as actuators and also as sensors. So what happens, essentially what you mean by that, so when a current is flowing, the length of this rod, whichever is there, so current is flowing through this wire, and this material which is making up this rod, the moment the current is flowing, the length of the rod is going to change by a small amount, delta L. And this strain is called the magnetostriction, and for which the symbol lambda is generally used. It's a second order effect. So the principal magnetostrictic effects which are observed experimentally, these are Joule effect. So these can be an extension or a contraction in the same direction as the magnetic field or in some other direction. Then you have something which is known as the volume effect. a volumetric expansion, which is a very weak effect. Then you have Wiedemann effect, which is a shear strain response to the magnetic field, which is analogous to tensile or compressive strain, which is produced in the Joule effect. And then you have something very important, which is known as Villari effect. This is a change in the magnetic permeability in response to a applied stress. So this is also referred to as the magnetostrictive effect or a magnetomechanical effect. So why this magnetostriction occurs? So when you have an external magnetic field, the domains which are aligned most closely to the external field, they will grow, while all the other domains are going to be reduced in size. So depending on the orientation of your crystal, there will be cases where electron orbitals, they cannot become aligned to the direction of the external magnetic field without a change taking place in the distance between the atoms or ions. So these distances must increase in order to become the orbitals get aligned. So these changes in length may cause the crystal structure to become either elongated in the same direction as the magnetic field, or it can become elongated in one or more direction at right angles to this direction. So in the second case, what happens is in some cases you might also see a contraction of the crystal in the same direction as the magnetic field. So that is why the change is not given as delta L. It can increase and it can decrease depending on the material which is being used. Then another very important term, it is magnetoresistance. So here the resistance of a conductor changes when you are placing in an external magnetic field. And this resistance is high if the field is parallel to the current, and it is low if the field is perpendicular to the current. So in general, the resistance depends on the angle between the current and the magnetic field. And obviously, as you know, because it is changing with the direction, it is known as an anisotropic magnetoresistance. This change is usually small, 5% only, but it can also be large, almost like 50% in case of some ferromagnetic uranium compounds. Why does this arise? It arises from a larger probability of the SD scattering of electrons in a direction parallel to the magnetic field. And this kind of AMR effect or anisotropic magnetoresistance effect, this is used in magnetic field sensing devices. So coming to nanomaterials, the magnetism is the most of the magnetism material right now we see are concentrated in the nano field. So why it is so? Because magnetism, they show a lot of changes when you go into the nano region. So magnetic nanostructures in bulk materials. So even in bulk magnetic materials, there are some structures which can be in the nanoscale, like the domain walls, as I said, in a ferromagnet. They are having nano dimensions. Then some domains, some magnetic domains basically, especially which are those in the vicinity of the surface or grain boundaries, they themselves can be nano sized. Or you can have some spin clusters, as I said, even above the Curie temperature, some paramagnetic material do have some spin clusters. So they can also be nanosized. So these are examples of magnetic nanostructures in bulk materials. So now when we go from bulk to nano, only the structure sensitive magnetic properties, which are the most structure sensitive magnetic properties, coercivity. So they are expected to change significantly. So some of the possibilities when we go from bulk to nano are the ferromagnetic particles become single domain. Superparamagnetism occurs in small ferromagnetic particles. Then giant magnetoresistance effect you see in hybrids, which is in layered structures. And then antiferromagnetic particles, they start behaving like ferromagnets. So these are some of the changes we see when we go from a bulk magnetic material to an actual nanomaterial. Apart from the fact, we also see some magnetic nanostructures in the bulk material, as I discussed earlier. So dependence of magnetic moment on the dimensionality of the system. So there is an increase in magnetic moment as we decrease the dimensionality of the system. So this is indicative of a fundamental difference in magnetic behavior between nanostructures and bulk materials. Why this happens? Because surface spins are usually not ordered along the same direction as the spins in the interior of the material. So in nanocrystals, more of surface has, this surface spins which are not ordered along the same direction as the interior. And so what happens is in case of nanomaterials, you have more amount of this magnetic moment compared to that of bulk materials. So as you can see, iron, normally you will find that it has a maximum possible magnetic moment of 6 Bohr magnetons per atom. So if you are reducing the size, you will find iron there is an increasing magnetic moment. In the bulk, it is only around 2.27 because the entire amount of the magnetic moment is never realized. But if you're decreasing the size, you find that the magnetic moment increases to almost 4. So this implies that in case of zero-dimensional nanocrystals, very little of the orbital magnetic moment is quenched. This is very much quenched in case of the bulk materials. So nanomagnetism, the surface effect is spin glass and volume effect is superparamagnetism. Spin glass we will not discuss much, but superparamagnetism definitely we'll discuss a little bit. So you consider a single domain particle with a uniaxial anisotropy. So the variable part of the energy is given by this particular expression. It is delta EA sine square theta, where delta EA is equal to what? This delta EA is nothing but your anisotropy energy, which we already have discussed before, which is KUV, and theta is the angle between the magnetization and the easy direction. So this theta value can be 0 or 180 degrees, because it is the direction of the minimum energy. And these directions, as we have seen, are separated by an energy barrier of the height delta EA. So the magnetization will remain stable and it will lie along these directions unless some perturbing force exists that can take the magnetization over that energy barrier. So thermal agitation may provide such a perturbation. So this process is likely to occur if the volume V of the particle is small, so that the height of the energy barrier is lower. So this V. Volume is small, so the height of the energy barrier is lower, and or if the temperature T is high. So if the process does occur, the time average of the remanence will be 0. So particles whose magnetization changes spontaneously are analogous to paramagnetic atoms, except that their magnetic moment in this case is much larger. So that is why these particles are said to exhibit nothing but superparamagnetism. So as the size of a particle is reduced, the whole particle becomes single domain below a critical size. So you can understand this in two distinct ways. A particle which is smaller than the domain wall thickness cannot sustain a domain wall, and the magnetostatic energy increases as r cube, which is the radius of the particle. Domain wall energy is a function of r square. So there must be a critical radius below which the domain walls are not stable. So the general trend is Rc is given by this particular equation, where sigma is the magnetic moment per unit mass and ms is the saturation magnetization. So you see, this is how the Rc or the critical radius looks like. So if in the Néel relaxation process, the relaxation time of the magnetization between these two states is given by a thermal activation or Arrhenius law. So the tau is nothing but tau is equal to tau 0 exponential delta EA by kBt. So what is the kB? kB is the Boltzmann constant, and T is nothing but your temperature, and tau is the average length of time that it takes for a ferromagnetic cluster to randomly flip direction as a result of thermal fluctuations. And EA is the anisotropy energy, which is again proportional to the volume. And Ku is the uniaxial anisotropy constant, V is the particle volume, Hk is the anisotropy field, and it is defined by 2 Ku by Ms. All these terms I have discussed before, and Ms is the saturation magnetization of the particle. So now if we have this, and if the particles are assumed to be non-interacting, then this blocking temperature or Tb, this is given by this particular equation, which is tau m is tau 0 exponential delta EA by kB Tb. So in this particular case, delta EA by kB Tb is nothing but this value. When you put in all these different values as I have shown in this particular slide, it is nothing but around 25. So delta EA is approximately 25 kB Tb. So kB is the Boltzmann constant, Tb is your blocking temperature, and the fluctuation. So when below the blocking temperature, which is Tb, which is of the order of this EA by 25 kB, the fluctuations between these two states become long enough to be observable on a lab time scale. And this is what we measure using the ZFC and FC curves. When you're looking into magnetic materials and nanomaterials, this is a very important study which we do, which is known as magnetization versus temperature. And here this A curve is known as the zero field cooling, as you can see over here, and you have FC, which is the field cooling. So you are plotting susceptibility versus, you are actually plotting your magnetization versus your temperature over here. And what you see is the FC and the ZFC. There is a particular point where the ZFC curve shows an inflection, and this particular point is nothing but your blocking temperature. So if the particle size is sufficiently small, then above TB, what happens above the blocking temperature, thermal fluctuations will dominate, and the particles can spontaneously switch its magnetization from one easy axis to the other. So such a system of superparamagnetic particles does not show hysteresis in the image curve above the blocking temperature, and hence the coercivity as well as the remanence both are zero. Moreover, the magnetization curves measured above the blocking temperature, they are expected to superimpose on each other when it is plotted as a function of this external field versus your temperature. So, above TB, if all the particles have the same volume V, the magnetization of the superparamagnetic particles is given by this particular equation. And when the system is in a block state below TB or blocking temperature, the magnetization of the ferromagnetic block state is given by this equation. So these are the two different equations which are there when you have the magnetization or of the particles which are shown above TB and when it is below TB. So ZFC and FC plots. So this region 1, which is known as the isothermal relaxation. Region 2, this is known as the isochronal relaxation under field. And above T, irreducible, this is this tau value is so short that thermal equilibrium is always attained before completing a single measurement. So this is known as the superparamagnetic state. And this TB value over here, as you see over here, with T reversible T max, or which is nothing but the blocking temperature. So from here you will get the temperature above which you will find this material to behave as superparamagnetic. So how you record the ZFC and FC curves? In case of zero field cooled, what you are doing is you cool the sample in zero field from T1, so where all particles are superparamagnetic, to T minimum. Then a small measuring field is applied at this T minimum. Then the sample is heated from this T minimum up to a high temperature and the magnetization is measured. So this is the ZFC magnetization. In the field cooled case, what you do, sample is cooled under an external magnetic field from T1 to T minimum at a constant rate. And then again the sample is heated from T minimum to high T and the magnetization is measured. This is FC magnetization. So if you look into the different hysteresis loops, all what we discussed so long, in the ferromagnetic state, this is the blue colored one. This is an ideal ferromagnetic material. This is how your hysteresis is going to look like. In case of a paramagnetic material, it is this green plot as you see over here, this green line over here. This is how a paramagnetic material looks. You will see some saturation magnetization, but this is very much less compared to what you see in case of superparamagnetic materials. So in this particular case, this entire material, it forms into one domain. All these domains move together as a single domain, and that is the reason why what you observe is something which is known as superparamagnetism, and the saturation magnetization value is very high. But both in paramagnets and in superparamagnets, you don't find any coercivity, you don't find any remanence. So now we talk about the domain wall motion and how the coercivity changes. So when you have a multi-domain material which is around here, you see an increase in coercivity with decrease in size. So from the multi-domain, as you are moving into single domain, as the domain size is decreasing, what you find is there is an increase in the coercivity. When it goes to a single domain, in that case, you will find the highest coercivity as is shown over here. In the single domain case, when you reach the single domain case, what happens? As you keep on decreasing the size in the single domain, the coercivity value, it starts decreasing. So, and when it reaches a very minimum size, in this case, this particle size, you can see over here, then it almost goes into a zero coercivity. So this is how the coercivity changes when you move from a multi-domain to a single domain. So from the multi-domain to the single domain, you have domain wall motion. Whereas when you come into the single domain, from the single domain, as your size, as the coercivity value decreases, because the thermal disordering effect, it becomes much more prominent in this case. And then ultimately what you have is a domain wall rotation, and ultimately thermal disordering effects dominate over tendency for spin alignment. And ultimately what you get is a zero coercivity. So what are the different applications of superparamagnets? It's in hard drives. The superparamagnetic limit refers how superparamagnetism limits the storage capacity of hard drive disks by setting a minimum size for the magnetic grains used. So what do you mean by this? In HDD, data or the bits, they are stored on platters of concentric tracks as a sequence of magnetization direction changes. Reading these platters refer to translating the magnetization into a voltage, and writing is just the reverse process. So you convert the voltage to a magnetization. So within a single bit cell, there are many magnetic grains. Now, in order to decrease the transition noise, the size of the magnetic grains has to be decreased. But if you now make the grain sizes too small, what is going to happen? They will become superparamagnetic. So magnetic grains retain data by holding the magnetization given to them during the writing process. But if the grains are too small, thermal fluctuation will cause the magnetizations to change. So that is why superparamagnetic limit, it refers to how superparamagnetism, it limits the storage capacity of hard drive disks. So that's very important to know the superparamagnetic limit. Then something known as ferrofluids. So ferrofluids are what? These are fluids in which evenly dispersed magnetic nanograins, they stay suspended in the liquid. So ferrofluids have another mechanism aside from the Néel relaxation that changes the direction of the particles' magnetic moments, which is known as the Brownian relaxation. And this causes the grains to physically spin due to collision with nearby particles. So when ferrofluids are placed in a strong vertical magnetic field, they experience normal field instability. By trying to align their magnetic moments with the field lines of the external field and field lines of their neighbors, the magnetic particles move in lines along the external field lines, resulting in spikes formed on the liquid surface. So you have to be again, be very careful about the superparamagnetic properties of these ferrofluids when these nanoparticles are being used as ferrofluids. There are many applications of ferrofluids in heat transfer, in loudspeakers for cooling the voice coil and damping by increasing the viscosity of the liquid flow due to an effect which is known as magnetorheological effect. So these are the different applications of superparamagnetars. Then you have magnetism in thin films or hybrids, as I said. They can have a 2D versus a 3D behavior. So suppose you have a nickel film which is deposited on a copper 100 substrate, and the thickness of this nickel film is greater than 7 monolayer. Then the system will behave as a 3D Heisenberg ferromagnet. But below 7 monolayers, it behaves like a 2D system. So in the 2D system, what happens? All the spins are in plane. Whereas in a 3D system, it is going to be out of plane spin orientation. So Curie temperature of thin films. So in case of, suppose a iron thin film is grown epitaxially over a silver substrate, the Curie temperature reduces from bulk values. At the bulk, you will have some values, but when you have a thin film, the Curie temperature reduces to almost only 100 kelvins for a 1.5 monolayer film. Why? Because in this case, the thermal disordering effect is becoming more prominent. So that is why your Curie temperature, it decreases. So due to exchange coupling of spins across an interface between a ferromagnetic phase and an antiferromagnetic phase, there is a preferred direction for the field, and this leads to a shift in hysteresis or the MH loop. Now we are talking something known as exchange anisotropy. Normally what you will find in a ferromagnet, the hysteresis curve, when you look into the hysteresis curve, what you see, it is equal on both sides. But in some materials, what you will find is that it looks like this. So in one side it is more, in the other side it is less. So this is the result of something which we call as exchange anisotropy. So this is what we are explaining right now. So there's an exchange coupling of spins across an interface between a ferromagnetic phase and an antiferromagnetic phase. So as a preferred direction for the field, and this leads to a shift in the hysteresis or the MH loop. So steps involved in creating exchange anisotropy, let us go through that. So you have a single domain ferromagnetic particle, which can be suppose cobalt, which is in contact with an antiferromagnetic layer, which is cobalt oxide. So you apply a field above the Néel temperature to this antiferromagnetic phase, and you saturate the ferromagnetic phase. Then you cool the system below the Néel temperature of the antiferromagnetic phase, and you introduce a preferential alignment of spins across the interface that is in the antiferromagnetic phase. The spin in the ferromagnetic phase will maintain their orientation even after the field is removed. Now you construct the usual MH loop. So if the field is removed, the spins of this ferromagnetic phase will flip to the field-cooled orientation due to the influence of this antiferromagnetic phase. Now as the field direction is reversed, the spins which are there across the interface in the antiferromagnetic phase with a large crystal anisotropy, they will oppose the reversal of the spin in the ferromagnetic phase. Hence, the exchange coupling will lead to a very high coercivity value. So this all what I said in the previous slide is explained diagrammatically over here. So in the A case, you see a preferential ordering of the spins in the antiferromagnetic phase across the interface. So CO is antiferromagnetic, so there is a preferential ordering. Whenever there is a field which is applied in opposition to the magnetization of the ferromagnetic phase, as you see the ferromagnetic phase over here is cobalt, it is in this direction. Here you're applying edge down. So what is going to happen? So this particular ferromagnetic phase is now going to align itself in the opposite direction. The moment it is aligned, then obviously in this antiferromagnetic part also some change is going to happen. So this will lead to a disturbance of spins across the interface and the antiferromagnetic phase. And this is what is manifested as the shift in this coercivity. So this is what is known as exchange anisotropy. And this is what you observe when you have a layered ferromagnetic phase with an antiferromagnetic phase. So whenever there is an interlayer of something like this happening, this manifests in the MH loop as an exchange anisotropy, and this you can make out very easily from the hysteresis loop. So I think with this today I'll come to an end for the class. If you have any questions, you can forward it to me. Okay, so in case there are no further questions, then we'll call it a day. Good evening to all of you. Enjoy the rest of your day. Thank you.